right, we're taking a look at some of the problems in the volume section. So the first problem is a rotational volume and is asking us to rotate the region bound by y equals x plus 1, y equals 0, x equals 0, and x equals 5 about the x-axis. So I'm going to go ahead and just shade this region. I went ahead and already drew it. Always start by drawing a graph and then shading that original region. So if I try to go ahead and draw what this region's going to look like after I rotate it, kind of more or less something like this, right? Again, when you draw these regions, doesn't have to be pretty, but it does help to give us an idea of more or less where this region is located. All right, so for this problem, I will be using the disk method. Volume is equal to pi times the integral of our radius squared dx. And so for our problem specifically, that will be pi times the integral. All right, so again, note here the domain for my region goes from 0 to 5, and so that's where the bounds on my integral come from. And then the radius that's being rotated here is the line x plus 1, quantity squared dx. All right, that's all that there's to it. All right, the next problem again is a rotation about the x-axis, and this time we have the region that is between the graphs of y equals 7 minus x squared and y equals 3. So again, if we try to kind of draw more or less what this thing would look like when we rotate it, might look something like this, right? So for this one, I'm going to use the washer method. Volume is equal to pi times the integral. So now we have big R squared minus little r squared dx. A few things that I want to point out. We are integrating with respect to x because we are rotating about the x-axis. And we have two radii, a big outside radius and a smaller inside radius. So for my problem, the big outside radius is going to be the graph of 7 minus x squared. So we'll have that quantity squared minus the small or the inside radius is the line y equals 3, quantity squared. And then finally, one last thing, again, we will need to put some bounds on our integral. So again, if you can answer the question, what is the domain of this region? We see that this goes from -2 to 2. So this is the integral that's going to calculate that volume. All right. Next up, we have a problem here that's giving us a region that is between the graphs of y equals x cubed, y equals 1, x equals 2, and we are rotating this about the line y equals -5. So we are not rotating about the x-axis, but we are rotating about a line that is still parallel to the x-axis. So I still want to use disk washer method, and I still want to integrate with respect to x. So one other small thing that I'm going to need to do here, I need to find that adjusted radius. And if you recall, we called that the functional radius. So this line right here, this distance, so this is the distance from the outside or the big radius to the axis of rotation. We're calling this our big functional radius. And the length of this line, the distance between these two, is always going to be top minus bottom. All right, so this guy on the top, this line right here, this graph right here, that's going to be my top. And that is the x cubed minus, and then on the bottom, we have this line right here, or the axis of rotation, that's going to be my bottom. So top minus bottom here gives x cubed minus -5. So this will just become x cubed plus 5. So we're looking for that distance. All right. I also need to find a small or an inside functional radius. So that's going to be, let's see, this distance from the inside or the small radius to the axis of rotation. So this distance right here. All right. And again, similarly, the small or the inside functional radius, to find a distance between two graphs, it's always top minus bottom. So this is y equals 1 minus y equals -5. So I get 1 plus 5. This is going to be equal to 6. So the formula that I'm going to use here, volume is equal to pi times the integral of big functional radius squared minus little or inside functional radius squared. This is equal to pi times the integral of x cubed plus 5, quantity squared, and then minus the inside, or the small functional radius, which is just 6, quantity squared dx. And again, finally, the bounds on my integral, go back and note what is the domain, essentially, of your region. We see here it goes from x equals 1 to x equals 2.